All right, moving on with the second part of 4.4 is we're looking at solving a polynomial function graphically. When we solve them graphically, we're specifically talking about the x-intercepts. So where it says this polynomial function p of x equals 0, we're talking about these x-intercepts on the graph. We're talking about greater than 0. Greater than 0 means above the x-axis. We've been working on that quite a bit. And less than 0 means below the x-axis. So we're going to take a second. We're going to go over to Desmos, and we're going to look at this in Desmos. All right, so here we are in Desmos. When I say the polynomial function equals 0, I'm talking about those x-intercepts. And it did say round to the nearest hundredth. This one, when it talks about solving graphically, that's when it's okay to go ahead and use the decimal form. And notice this function, it was all decimals, so that's another indication to you that we'll be using decimals. So it says round to the nearest hundredth. So when I round, I have x equals negative 1.37 because that ending number was an 8. I have x equals 0.33 because the ending number was a 2. And then the last one I have x equals 2.32 when I round. So now let's talk about the next part of it where it said the function is greater than 0. When is this polynomial function greater than 0? That means when is it above the x-axis? So I'm going to trace over it. It's above the x-axis, all of this stuff between those two zeros, and then it's above the x-axis after the last 0. So we're going to write that in interval notation. So we have between negative 1.37 and 0.33. And then we also have from 2.32 onto infinity. Keep in mind, these are always domain numbers. We're saying over what domain is the function above and below the axis. So now we're going to do the next part. When is the polynomial function less than 0? Less than 0 means below the axis. So we're looking at all of this stuff prior to the first 0. So I have negative infinity to negative 1.37. And then also between the last two zeros. All of this is below the x-axis. So then we're going to say and from 0.33 to 2.32. Keep in mind we're learning to read that notation. When I say the function of greater than or less than 0, I'm saying above or below the x-axis. All right, next question, solve the inequality. So the first thing we need to do, if we're doing this by hand instead of in the calculator is going to give us those decimal approximations, and in this class we're not looking at those decimal approximations, so we're going to have to expand this out. So if I expand this out, I have 2x squared minus 2 plus 4x squared, going to be minus 2x, and we're going to combine some like terms. So I have 6x squared, I have minus 2x minus 2 equals 0. So we might think to ourselves real quick, does this factor? It might be factor friendly. If I do AC, I get 12. So I'm thinking real quick about the factors of 12. I have 1 and 12, I have 2 and 6, and then I have 3 and 4. I need to say to myself, do any of those guys make a 2? And if I look down my list, no, they don't make a 2. So my next option is maybe I can complete the square. So while those are all even numbers, I don't want to divide a 6 out of those 2's because now it's going to be a fraction 1/3. I don't want to cut 1/3 in half and square it, so I'm not going to use complete the square. I'm going to go ahead and use the quadratic formula to find these zeros. So the quadratic formula says opposite of b, so it's negative 2, so I'm going to do positive 2, plus and minus the square root of b squared. So be very careful if you're using the calculator. Negative 2 times negative 2 is a positive 4. You're better off to just do that part in your head. A is 6 and C then is negative 2 all over 2A. So 2 times 6. Or do some math here. So I have negative 24 times 2 is negative 48, or positive 48, because negative times negative, plus 4, so it's 52. So I have 2 plus and minus the square root of 52 all over 12. And you might think you're done, and you might be, but if we need to reduce this, 52 does divide by 4. It's 4 times 13. So I can actually reduce that. This is going to be 2 plus and minus the square root of 2 root 13 all over 12, which gives me some friendlier numbers than 1 plus or minus just root 13 all over 6. This is the reduced version of those zeros. All right, so if we look at solving B analytically, we're saying when is that function less than 0? So we need to interpret what this less than 0 means. That means below the x-axis. So let's think about what this parabola looks like. So if I think about the parabola, 6 is a positive number, so it's going to open up, and we do have real solutions. So even if I did not have the graph sitting there, a visual image of the graph would be something like this. And so without actually graphing, without actually finding those numbers, without going to the graph and actually putting into Desmos, we know that all of the stuff below the x-axis is between those zeros. So how do I write that? Well, the first thing we need to do is indicate which one is this one back here, this furthest one negative. Well, if we just think about it, it would be the 1 minus square root of 13 over 6. So that's the furthest negative, 1 minus square root of 13 over 6. And then the furthest one, this is the one that's positive, well, that's going to be the one where I add. So 1 plus the square root of 13 over 6. Those are that's the space between the two zeros in the exact form. We're going to use the exact form. If you give me decimals, I'm going to mark it wrong. The goal for this course is to be able to give me the exact numbers. All right, example 7, find all the 6 complex sixth roots of 64. So this sounds crazy. But it's not so bad if we write it in function form and then just let our math tell us what to do. So this is x to the 6th power. Something to the 6th power is 64. So there's a couple ways to do it. The way I'm going to start is with x to the 6th minus 64 equals 0. Because this x to the 6th, that is like 2 cubes. So I can break this up into x to the 3rd minus 8 and x to the 3rd plus 8. So we started out treating it like breaking into cubes, like a difference of squares, where x to the 3rd and x to the 3rd are quote-unquote squares. But now, if you think about what we learned in the last chapter, that's a sum and difference of cubes, which means both of those things break down. So this first one breaks down into x minus 2. X squared is going to be plus 2x plus 4. And the second one is going to break down into x plus 2, x squared minus 2x plus 4. So let's find some zeros. Well, we have some friendly ones. We have x equals 2 from this one, and we have x equals negative 2 from this one. But then, like what was on your assessment from chapter 2 or chapter 3, we have some imaginaries coming from these quadratic factors right here. So if we use the quadratic formula, opposite of b, so negative 2, plus or minus the square root, 2 squared is 4, minus 4, a is 1, c is 4, all over 2. So negative 2 plus or minus square root looks like negative 12 over 2. Well, negative 12, that'll reduce. And 12 is 4 times 3. So this could be negative 2 plus or minus 2I root 3 all over 2, which is then going to give me negative 1 plus or minus I root 3. So there's 2 of them. Now, I don't want to keep doing a lot of extra work. There's only one thing that's different from the pink quadratic equation to the green quadratic equation, and that is all of a sudden it's a minus 2. So when I do opposite of b, it's going to be a positive 2. And again, we don't want to keep redoing unnecessary work. So I'm going to go ahead and write it, and then we're just going to skip to the answer. So if you look at what's underneath that radical, that square root thing, that's all going to be the same. The only thing that happened is instead of a negative 2 in front, I have a positive 2 in front. So the other 0 is going to be 1 plus and minus I root 3. So there is actually 6 of my zeros, all 6 of them. If I list them out, I have x equals 2, x equals negative 2. Those are the real ones. And then I have 4 imaginary ones. So I have x equals negative 1 plus root 3, or I root 3, sorry. I have x equals negative 1 minus I root 3. I have x equals positive 1 plus I root 3. And I have x equals positive 1 minus I root 3. Those are all 6 of my zeros. So there's some creative factoring going on to solve problems like this. You should probably star this one. All right, and then we have the last application problem. So we have a cardboard box that we're going to cut squares of a certain size out of the corners. So this is kind of like the one that we did in the last chapter. Only in the last chapter I told you what size those squares were. Now I'm not going to tell you what size those squares are. We're just going to write the equation and see some different volumes for the box, depending on what size those squares are. So it says, if x represents the length of each side of the square cut out, determine the function v of the volume that describes a box in terms of x. So they are cut those squares out, and then we're going to fold up the sides, and we're going to make an open top box. So volume is length times width times height. So we have a height, we have a width, and we have a length. So we're going to go ahead and just write that. We're going to multiply all 3 of those terms. And the 20 and the 12, that comes from the original size of the paper, the cardboard that we're cutting. So that we said minus 2x because it's minus an x for each of the length and width. So that's where the minus 2x thing is coming from. So this is our volume. I'm going to label this as v of x. So the function v means volume. Now it says to graph this in a 0 by 6. This is our domain. And a 0 by 300, this is our range. So keep in mind in a real world problem, if x is the size of the square we're cutting out, I don't need negative squares that I'm cutting out. We're doing taping it on there. I don't need negative volume. So the volume, the real problem exists only in this positive quadrant. So we're going to go over to Desmos and we're going to look at this graph. Okay, so here we are. We have our Desmos graph. It's kind of a blown up version of the one that we had on the page previously. But it says to what is x for the volume of the box to be maximized. So x is the size of the square cut out of the box. Y is the volume. So that's our xy pair. So if I pick any point on the graph, the x is the size of the square. So if I pick this point right here, let's say 1, when the side length of the square is 1, the volume of the box is 180. So the next question is, where's the volume maximized? The nice thing about Desmos is it gives me this little grayed out dot. That is the maximum point right there. So the square that will maximize the volume is the square that is side length 2.427, and the associated volume is 262.682. So this is our square, and this is our volume right there. And then the next question asks us, for what values is the volume equal to 200? When is it greater than? When is it less than? So I went ahead and graphed this line to 100, and these intercepts right here are going to show me when is it equal to. So when is the volume equal to 200? This is very similar to the greater than and less than 0 problems we've done. So the side length of the square that equals a volume of 200 is 1.174, or we could get bigger on the other side and do 3.898. Please don't call that 4 because it's not 4, it's 3.898. Or 3.9, it's not 3.9. Okay, the next question is when is it greater than? So what values make it greater than 200? So greater than 200 again is above this line. The same way when we do greater than 0 is above the x-axis, greater than 200 is that piece above the line. So if I said the volume is greater than 200, I'm looking at anything between those two x values that I just solved for. So anything between 1.174 and 3.898. So if I said make a box that has a volume of at least 200, as long as you pick something between there, you could do 2, 2.5, 2.25, 3, 3.5. Any of those would be greater than 200. So especially if we think about doing this in the real world, we would want to pick numbers that were like easy for us to find. We wouldn't want to try to actually measure out 1.174. Like that would not be friendly. Then the next part of it, when is it less than 200? So if I told you to find an x value to cut out the size of the square that's going to make it no more than 200. So that's the same thing as less than. That's all of this stuff all the way to the 0. So keep in mind this is a real world problem, so I can't say negative infinity. This definitely starts at 0, and it's not equal to 0 because if I didn't cut any square, I don't have a box. And then on the other side is 898. And then this ends, it definitely has an ending point. It's not to infinity. The biggest size square this has is 6. So that is the greater than, less than stuff with a number other than 0, but it works the exact same. It's just how you interpret it.